All right, welcome everybody. Let's get started. I want to remind you that your next homework assignment is due the same day as our first exam. And just on the subject of the exam, you don't need to make an equation sheet because I'm going to provide the one that's already on MU Online. I don't know if you've had a chance to look at that, but it has all the formulas we've used so far in this semester that you'll need for the test. And the test is going to just be 75 minutes long in class. That's a week from today. So today we're going to be talking about buoyancy for the most part, but we have an in-class exercise that I've just been handing out to you. And this was a test question, I think, 3 years ago. So it gives you kind of like a feeling for how the test questions are formatted and the length of them. But I turned it into an in-class exercise so that you could get some additional practice working on problems related to curved surfaces, hydrostatic forces on curved surfaces. So let's begin the class with that. In the same way that we did last time I had one of these handouts, I'm going to pause the recording, give you some time to work collaboratively with your classmates, and we want to know for the horizontal forces, both the magnitude and the location. So that's A and B. The horizontal forces acting on the curved gate. And then for the vertical forces, just to keep the time to a minimum, let's just calculate the magnitude but not the location. Because for the location of the vertical surfaces, we'd have to do that kind of like weighted average thing, and that sometimes takes a bit of extra time. So we'll just do, for the vertical forces, the magnitude. Okay, let's look at the solution on this one. I think if you haven't already solved it, hopefully you're at least headed in the right direction. I wrote on the whiteboard here a couple of key hints. I mentioned earlier that this was an exam problem in a previous semester, and one of the things that I'll often do in an exam problem is have some sort of like preliminary conversions that you need to do before you jump into the main body. And in this case, the preliminary conversion that you needed to do is related to the given density. So the density is given in terms of kilograms per liter. And there are 1,000 liters in a cubic meter. So if you multiply this density by 1,000, then we'd have a density of 745 kilograms per cubic meter. But we don't need density to find the force, the hydrostatic force. We actually need the unit weight, gamma. And so to convert between density and unit weight, we simply multiply by g. And so the units of unit weight are going to be newtons per cubic meter, because when we have g, which is meters per second squared, multiplied by kilograms per cubic meter, then it cancels out to newtons per cubic meter. Okay, so those preliminaries can sometimes be the easy part, sometimes they can be the hard part. Maybe you don't know exactly what to do on the hydrostatics. Well, at least you can convert the density into something usable. And if you've got a density, you might as well calculate a unit weight. And so you do a couple of those just early on things, and then if you're like kind of stalling, then maybe it'll dawn on you the main thing that you're supposed to be doing. All right, so here's the solution from that a couple of semesters ago. I apologize that the writing quality isn't quite as clear as I'd like it to be, but what we do is we find the depth of the centroid of the projection. Now this is a curved gate that's 2 meters tall and 4 meters wide. And if I go back to here, this 2 meter radius dimension also rotates up to be 2 meters, which means the vertical projection of this curved surface is a rectangle that's 2 meters tall and 4 meters into the page, so 4 meters wide. That means the depth of the centroid will be the 3.7 from the water surface to the edge, and then another 1 meter down from this edge to the center of area of the projection. Okay, so we calculate the force. The hydrostatic force should be 274.8 kilonewtons. That's the magnitude. It's just the pressure of the centroid multiplied by the area of the projection. And the area of the projection is 2 meters tall, 4 meters wide. All right, so that's the horizontal force. The next thing it asked for was the location of the horizontal force. And since that's a vertically oriented rectangle, the y bar is equal to delta h, and so y bar is 4.7 meters. And so in calculating YCP, then we use the 4.7 as the y bar. We have to calculate I, which is area moment of inertia. The formula is AB cubed divided by 12. And if you don't remember what's supposed to be B, the parameter that's being cubed, it's the vertical dimension of that 4 by 2 plate. So it's 2 meters tall, 4 meters wide, so we cube the 2 meters since that's the vertical component. The area moment of inertia is 2.667 meters to the fourth, which is what gets substituted in to the YCP formula. And in the end, the YCP, the depth to the location of the center of pressure, which is where that hydrostatic force is applied, 4.771 meters. So any questions so far on either the magnitude of the force or its location? The vertical forces, what do they depend on? The weight of the water above the gate. So if we go back to the drawing, there's going to be, we can break that shape up into two pieces. The rectangular piece above the gate and then that curved section above the gate. And that's what I did here in the solution. I said we've got a volume 1, which is the rectangular piece, 29.6 cubic meters. And then volume 2, I said there's another rectangle subtracting out the quarter circle. So, man, that's hard to read. 3.434 meters cubed. So then I find the weight of each one of those segments in terms of newtons, and then the vertical force is combining the two together. So the net vertical force should be 241.4 kilonewtons. And I didn't ask for the magnitude. So I guess that's another thing to point out on the exam is maybe in the homework you got so used to solving A, B, C, and then D. On the exam, maybe I only ask A, B, and C. And so I've had exams, just like, I think on this problem, I had students spend 15 minutes trying to find the location of the vertical forces, and it wasn't asked for. And they burned up all kinds of time on the test solving for something that wasn't part of the question. So please be sure that you read carefully. Yeah. So it's basically the weight of the water above the gate is what I'm trying to find. And so I say, I know the weight of the water above the gate depends on the volume of the two components. Component 1 is the rectangular shape that's above here. So let me switch back to the better looking drawing. So the water that's above this gate is one rectangular segment that's 3.7 meters tall, 2 meters wide, and then 4 meters into the page. So I think it's like a box of water. And then I've got this sliver of water above the gate that is essentially a rectangle minus a quarter circle. And then that shape projected 4 meters into the page. And so the dimensions for that are what I was calculating here, where I said 2 by 2 by 4 minus pi r squared times 4 divided by 4. Because times 4 is the depth into the page, divided by 4 is the fact that it's a quarter circle. So then the net volume of that sliver segment, the curved shape that's immediately above the gate, is 3.434 cubic meters. Other questions before we get into buoyancy? Yes? Okay, good question. Yeah, what if it had asked for the location? It didn't, but if it had, let me draw the shape of it. So we've got this gate. So if it had asked for the location of the vertical forces, you'd say, well, I've got this is in the middle, the rectangular element above, and you'd find out the magnitude of that and its location. So since that is, the radius of curvature is 2 meters, it's 1 meter from the edge. So that force is 216.3 kilonewtons. And then this one was 25.1 kilonewtons. And you'd need to find its location the same way that we did in class the other day, where we said the location to the centroid of the quarter circle is 4r divided by 3 pi. Was that it, or was it 4 pi divided by 3r? Anyways, you've got the formula, 4r divided by 3 pi. You've got the formula for the location of the quarter circle, and we know the location of the rectangles in the middle, and so you'd use the weighted average technique to find out where that component is. And then you would do another weighted average to say I've got this much force in the middle and this much force offset sideways. And you'd multiply the magnitude by the location and divide by the total magnitude. So I won't go through all those steps right now because we need to move on to buoyancy, but if you do want a refresher, that was the second half of the lecture that we did on Tuesday, and the video's on there. It's a whole thing, which is why I didn't include it on the examples, because it would take more time than I wanted to just give you the first taste on this of what the exams look like. All right, so buoyancy. Here's an interesting picture from Charleston. We've got a gas station, and it looks like a submarine has surfaced right in the parking lot of the gas station. But it's not a submarine. Anybody want to guess what that is? It's their gas tank. I mean, I guess that's the most logical explanation, right? And this gas station was closed, and so there wasn't any fuel in the gas tank. So that's an important thing. Anyone want to speculate what happened? What do you, okay, you're right, but explain. Go into more detail. Why did the groundwater raise it?
Because the tank had a lower density than the water in the ground, and as the water level rose, the tank rose.
All right, so when it's wet weather, the water level underground rises and falls. Depends on how much rain we've had recently. And so the water table isn't just a static thing. The water table varies depending with the weather. And so when the gas tank is nearly empty, then the overall mass of that tank, including the container and the contents, is going to be low. But the volume of the tank doesn't change. So that means the density of that tank is changing depending on how full it is. And the buoyant force, the force pushing up on that tank, got really high when the water level rose. Here's another picture of it, just to give you the view of this tank that emerged out of it was enough buoyant force to break the concrete and asphalt. So near where I live, I noticed just recently somebody's installed a swimming pool. And the contractors who installed the swimming pool know about this, because the fence isn't around the swimming pool yet, and no one's using the swimming pool, but they filled the swimming pool with water. It's a little bit dangerous. I mean, a kid could wander around and fall in, but they filled it with water because they don't want that swimming pool they just installed to rise up out of the ground, which is what would happen if conditions got really wet and the water table rose enough. So trying to avoid the buoyancy. So this may not make sense yet, but it will in just a minute. Let's look at a video of a submarine coming out of the water. This is in Hawaii. Wait for it. Come on, YouTube. There we go. Buffering. Boy, the video's not this good. It's building up an artificial anticipation that really is undeserved. Okay.
0, -1. Oh, those are Maui seconds. Oh, there he is, too! Oh, Red October.
Why did it stop? Why didn't it keep rising even more? More dense than the air. Yeah, it's not going to float away. Bye-bye, right? It's submarines. It's not the Goodyear blimp, right? It's a submarine. But, I mean, why didn't it rise one more foot? It rose, I don't know how deeply submerged it is. Maybe it keeps going and going, but it was underwater, and then it started rising. Why did it stop rising? Perfect. That's the perfect answer. It reached equilibrium, meaning that the gravity forces, the weight of that submarine going down is equal to the buoyant forces that are lifting it up. Well, what about here? How come we don't see it at this point? Why aren't we seeing the submarine right now? It's in a different equilibrium, right? So the way that a submarine rises and falls is partly dependent on ballast tanks inside the submarine. And so they'll pump water into the submarine inside those ballast tanks when they want it to dive. And then they'll pump the water out of the ballast tanks when they want the submarine to rise. And so buoyancy is the key factor there. Now, buoyancy is really easy to calculate. The buoyant force is dependent on the volume of water displaced and, more specifically, the weight of the water that's displaced. Okay, so let's consider this submerged object. It's an irregularly shaped object. There's going to be a variation of pressure acting on the outside of the object, and you'll notice the arrows are longer on the underside. Why are these arrows longer than the arrows on the top? I mean, on a fundamental level. I mean, they're longer on the bottom because that's how they got drawn. But, I mean, they're drawn to that length because that means something. Why is it that the arrows are longer on the bottom? The pressure is higher down there because it's deeper. We know that pressure increases in the direction as we go downward away from the water surface. So let's say that we could calculate the volume of that object, and we call that volume B. Volume A is the volume of water that's above it. So there are external forces that are acting on the object. There are forces down below it pushing up, and there are forces above that object pushing down. But the forces underneath it are larger because it's deeper on the underside than it is on the top. And so if we say we want to calculate the forces that are pushing the object upward, then those forces are going to take into account the volume of the object itself and the volume of the water above it. And this goes back to the idea from last time where we had like a tank of water that's like this. Here's the water level, and then there was this irregularly shaped wall. Okay, there was like this plate, and the forces were acting upward. And what I said was, you need to extend the water line over here, and so the magnitude of the forces are equal to how much water would have been above it. So what we're saying here, these upward forces depend on the weight of the water above the object and the weight of the water displaced by the object. So the volume of both of those bodies multiplied by the unit weight of the fluid that this body is in. Not the unit weight of whatever this object is made out of. We don't know what this object, maybe it's styrofoam, maybe it's marble, but all we're thinking about right now is the water to calculate the buoyant force acting upward. The forces pushing it down are just related to the volume of water directly above it, volume A. And so the buoyant force is the difference between the two. It's the difference between the upward forces and the downward force. And so it's the volume of the object itself multiplied by the unit weight of whatever this fluid is. So the whole rest of today is just this formula: buoyant force is gamma times the volume that's submerged. What determines if this floats upward or if it sinks? The unit weight of what? Whatever the object of the water is. We could say that a couple of different ways. We could say the weight of the object relative to the buoyant force determines whether it floats or sinks. We could say the density of the object relative to the density of the fluid, or the unit weight of the object relative to the unit weight of the fluid. Each one of those things is interrelated, but what determines if it floats or sinks from a force balance perspective is if the buoyant force is greater than the weight of the object. So if this is marble, it's going to sink because marble has a higher density than water does. But if it's styrofoam, then it's going to float up to the surface. It's not going to float away into the air. It's going to float until it comes into equilibrium, until the amount that's submerged causes the same buoyant force equal to the weight of that styrofoam. So let's say that we've got this box that's submerged. Just to prove the idea of buoyancy to you, that it really is the difference between the forces underside and the forces above. Let's say we've got a plastic cube that's 1 by 1 by 1, and it's submerged 3 meters below the surface. So from the water surface to the top edge of the cube is 3 meters. What I'd like you to do is calculate the force on the bottom surface, the force on the top, and then the difference between the two, and then calculate the buoyant force, just as the volume that's displaced. And so by displaced, what I mean is if this cube wasn't here in the water occupying 1 cubic meter of space, then water would be there. But this cube, it pushed water out of the way. It displaced water. And so by displacing the water, the buoyant force is equal to the weight of the water that would have been there if that block didn't displace it. This may be my best drawing of the whole semester. Look at that. Not too shabby, right, guys? All right. So what we do is we find the force on the bottom, which is going to be the pressure at that depth. So the pressure at that depth will just be 4 meters times the unit weight of this fluid, water, 9810. And then the area is 1 square meter, the bottom side area. So the force pushing up on the bottom, 39,000 newtons up. The downward force from above, we find the depth to that surface is 3 meters. So the downward force, 29,430. The difference between the two is 9810 newtons. Man, that doesn't scroll like I'm expecting. And the reason why it's that nice round number, 9810, is because the cube is 1 cubic meter. And so if we just have 1 cubic meter of water, and water is 9810 newtons per cubic meter, then that's why it's that familiar value there, is the difference between the two. And just as the proof that we can also just calculate the volume displaced multiplied by the buoyant force, 1 cubic meter times 9810 gives us 9810. So the buoyant, you don't have to always calculate the force from above and the force from beneath and the difference between the two. It's easy enough to do if it's a regularly shaped object like this, but if you have a curved object like you do on the homework with that plug that's plugging the hole, it would be really complicated to find the forces acting from beneath and the weight of the water above it, and much easier just to find the volume of that hemisphere instead to be the volume. To be the buoyant force, the vertical force, in other words. Any questions on this example? If this is plastic, we can presume that it's going to float to the surface. Most plastics are lighter than the density of water. So it probably hasn't reached equilibrium yet. This object is floating. And the point that I want to make is that buoyancy doesn't depend on the volume of the object itself, but buoyancy depends on the submerged volume of the object. So here, we're calling this volume D, just the submerged component. And so for an iceberg, for instance, it's the submerged volume of an iceberg that dictates the buoyant force. And the fact that ice expands when it freezes, that causes just a small fraction of it to be above the waterline and most of the iceberg to be beneath the waterline. All right, so to practice some of these ideas, let's say that we have a block of plastic that the physical dimensions of the block of plastic is 5 meters tall, 10 meters wide, and 10 meters long into the page, dimension that's not seen. And it's floating in water, just no temperature given, so we assume the unit weight of that water is 9810. I'm going to ask you to calculate some preliminary stuff like the buoyant force of the water that's acting on the object. Since we know that it's in equilibrium, it's floating in the water as shown. That phrase implies that it's floating in equilibrium. So the buoyant force is equal to the weight. F sub B equals W when it's in equilibrium, and we do have equilibrium. Based on the way that it floats, we can calculate and determine what is the specific gravity of the block. We're told that it's plastic, but we can find the unit weight of that plastic by just taking a look at the way that it floats. And so let me pause the recording so you can do each of these steps and find out the specific gravity of the block. Okay, so the buoyant force just depends on the submerged volume of the block. Now we can calculate the whole volume of the block, and we do in step 3. The entire block itself is 500 cubic meters. That's a big block. Sometimes I create these examples without really thinking about the scale. 10 meters, big deal. But this is a lot, 500 cubic meters. So of that, only 4.6 meters of its depth is submerged, and so this buoyant force depends on the submerged volume, or the volume of water displaced. That DISP means displaced. The displaced volume multiplied by the unit weight of the water. So it's in equilibrium, so the buoyant force is equal to the weight of the water, and the weight of the water is equal to the weight of the block. So later on here, where it asks for the specific weight of the block, the definition of specific weight is the weight divided by the volume. So you can calculate the specific weight for liquids, but you could also calculate specific weight for solids. You know, we can talk about the density of solids, so why not their specific weights? You know, and so here, that's what we do. We find the gamma of the block, even though the block itself is solid. So it's less than the gamma of water, which explains why it's floating. The interesting thing is that if you look at the ratio of the gamma of the block to the gamma of water, it's 92%, which is also the ratio of the percent submergence. It's 92% submerged. That's not a coincidence. The depth of 4.6 to 5 is 0.92 in the same way that the unit weight of the block versus the unit weight of the water. So there's a linear relationship between specific gravities and the percent submergence. All right, so we're going to take these ideas up to the next level. The idea of weights and force balance on this next example. It's a submerged shape that's a little bit unusually shaped, just the orientation of it. But before we move on to that next one, any questions about this? All right. So let's say that instead of just one thing, we have to keep track of two objects. This is actually a fun problem. We've got a wooden block floating up at the surface and a metal shape underneath, and they're attached by a cable. And this wooden block, it would float more except for it's being weighted down by this metal piece. And so we want to find out the tension in the cable that connects the two and the mass of this secondary object here. Here's what we know. We know the dimensions of the wood block. It's 10 millimeters by 50 millimeters wide by 50 millimeters into the page. You can see from the drawing that it's submerged 7.5 millimeters submergence, because it's 2.5 millimeters that's not submerged. So we can, from this, calculate the volume that's displaced. And the specific gravity of that wooden block is 0.3. Now, by knowing the specific gravity, you can calculate the weight of the block. So we're going to have to think about this being in equilibrium. What does the force balance look like for that upper block? We've got the water, we've got the block in the water, and so what are the forces involved? Okay, the tension, the cable. Is the cable pushing the block up or pulling the wooden block down? Okay, it's down. So we've got the tension in the cable. What other force is there? Okay, there's the weight of the block also acting down. And finally, buoyant forces are acting up. I'm going to move that over to the side here, F sub B. It's the location of that buoyant force would be in the center of the object, but I just don't want to draw the tension and the buoyant force on top of each other. So the force balance is that F sub B, which is up, is equal to the weight plus the tension in the cable. So that's this first one. Let's call that object 1. Okay, and then there's also object 2, that metal piece on the underside of that. We're given in the problem statement the volume of it, not the shape, not any of its dimensions, just the volume. But that's enough. That's okay for us because the volume is what's going to give us the buoyant force acting up. Let's do a force balance on it. All right. Tension is up. What else? Weight down. We'll call that W2, since this is object 2. I'll call the previous one W1 for the weight of object 1. F sub B 1. Do I need to have T1 and T2? No, they're connected to each other. So the tension that's pulling block 1 down is the same tension that's pulling object 2 up. So I'm just going to call it T rather than T1 and T2. And then finally, the buoyant force, F sub B 2, which is acting upward. So if we did the same sort of, yeah, go ahead. Do you have a question?
Need the weight of the water between there pushing down.
Good question. So you're wondering about like how far apart is it? What's the weight of the water? We don't need to do that because remember the buoyant force is the difference between the forces from above and the forces from beneath. So we're just bypassing that concern entirely, the difference between above and beneath weight of the water. So F sub B takes that into account for us. Is there another question? All right, so our force balance is going to be the weight of the water down, W2, not the weight of the water, the weight of the object down is equal to T plus F sub B2. All right, so here are the steps we can follow to solve this one. Find the buoyant forces on 1 and 2. What's the formula for that? What's the F sub B formula? Okay, the unit weight multiplied by volume displaced, V sub DISP, displaced water. So the unit weight of the block, the unit weight of the metal, the unit weight of whatever fluid is being displaced. So it's the volume displaced multiplied by the unit weight of what did that submerged object push out of the way since it is where it is. And in this case, it's submerged in water. All right. So find the buoyant forces, then find the weight of 1 based on the specific gravity and the volume. Okay, so we're told the specific gravity is 0.3 and we know the volume of it. Force balance, compute the mass of 2 from its weight. All right. I'm going to pause for a moment and let you kick the can down the road on this problem. Then we will look at the solution in just a minute. Yeah. All right. So the first thing that we see in the solution here is calculating the buoyant force of both of the two objects. The first object, the buoyant force, depends on how submerged it is, and this parameter of 7.5 millimeters by its other dimensions, 50 millimeters both in width and in depth into the page, multiplied by the unit weight. So 0.184 newtons. Who got that same buoyant force for the block, acting on the block? Good. The buoyant force of the metal part that's down under there, I guess the hard part of that is converting 6,600 millimeters into cubic meters. It's 1,000 millimeters by 1,000 millimeters by 1,000 millimeters to convert between millimeters and cubic millimeters and cubic meters. So we get the buoyant force of object 2, 0.065 newtons. Now, the weight of object number 1, if we're given the specific gravity and the volume, then we can calculate the unit weight of the block, and then from that multiply it by the volume of the block to find the overall weight of that object. Okay? And then doing the force balance, which we kind of already hinted at with the drawings on the board. We say in the vertical direction everything's in equilibrium, so the forces are equal. So the tension in the cable is just going to be, for the first object, the difference between the buoyant force and the weight. So we know the tension in the cable by first analyzing that wooden block, and then once we know the tension in the cable, that becomes a known during our analysis of object 2. And that's what allows us to calculate the weight of object 2. So the weight of it is going to have to be, by definition, equal to the buoyant force, which we previously calculated, and the tension from the previous step. And then just the definition of mass is we convert the weight is mass times gravity, so mass is weight divided by gravity. So it should be 0.0179 kilograms or 17.9 grams. Can anyone else confirm that? That's what you got? Yeah? A few shaking heads, good. Yeah? Close enough? Yeah, all right. In the 5 minutes that remain, I want to give you a couple of hints on the homework assignment. All right. So in problem 98, I put together this drawing because I think in this problem there isn't actually a drawing associated with it. And I felt like when I read through the problem statement, it's maybe something that would be easy to misinterpret. So here's a drawing that hopefully will help you to visualize what's going on here. We've got a submerged buoy, and it's connected to the seabed with an anchor chain that has a maximum force of 4,500 newtons. And we know the weight of the buoy. So here it's saying, like the outside metal of it weighs 1,200 newtons. And we know the diameter of the buoy, and assuming it's spherical, you can calculate the volume of it. And of course, that's what tells you the buoyant force. So you're going to need to do a force balance on this buoy, very similar to the force balances that we just looked at in this example. And then the question is, how much scrap iron needs to be in there so that we don't break the chain? Because presumably, if there's no scrap iron, the buoyant force is going to be so large that it would exceed the capacity of this chain to hold it down to the ocean floor. So we're going to have to load in a certain amount of scrap iron just so that this maximum force limit isn't exceeded in the anchor chain. So hopefully that helps you to visualize what's going on in that problem. Any questions before we move on to another one? All right. This is another one where they're describing it but not really showing what's going on, and I felt like some visuals would maybe help you out. We're taking this system, which is a block on a scale, and we're measuring what the scale says both in air and in water. So it's the same block, it's just that we're submerging it later on, and we're going to look at how the scale reading changes. And so when it's in air, the scale says 700 newtons. And you can think of that scale reading either as the weight acting downward, or it's the force of the scale pushing up on the block. And the reason why I encourage you to think about it that way, as you see here it's saying S2 pushing up, is because when it's in water, the buoyant forces are also pushing up on the block, and that's why we have a different reading. It's not because the block itself magically transformed into something that has less mass. It's just that the buoyant force pushing up reduces the scale reading from 700 to 300, and so those buoyant forces are making up the difference between the reading in air and the reading in water. Okay, so that's a hint for problem 100, is the before and the after is when it's measured in air versus when it's measured in water. And when it's measured in water, there's also a buoyant force. All right, that's it for today. Remember that your assignment's not due till Thursday of next week, so you've got some extra time, but I'd encourage you to get started early on that. I'll see you Tuesday.